Hi everyone, welcome to a recording on the solution to the green peppers example in this week's slides. In weeks 1 to all of the LP problems that we covered were in manufacturing, Mangurato manufacturing, doing windows, doors and tables, slicing cakes, doing black forest and red velvet cakes. We did also some examples in construction, so like the hotel rooms on the piece of land. The VW question is a manufacturing question. So those have been a little bit simpler in terms of the approach. This week, we're going into slightly more complex questions. We'll be seeing examples from the transport industry, blended industries, investments, and these particular sectors have a lot of constraints to consider or a lot more nuances within their constraints to consider. Now, the green peppers example is a good one to start with because it's intuitive. I would like you guys to always try and put yourselves in the shoes of this person and what this question sounds like to the owner of a transport company. Okay, so it is not a foreign concept. It is not difficult if you are able to relate to the question. So the green peppers example is below. This particular video will just be the LP setup for this question. I'll do a second video on how to do the solver setup for the question. Okay, Green Peppers is a company. They need to send their goods to 4 customers. Each customer has an order waiting to be delivered, but the ops manager must decide on how much of each order to send to each customer from the 2 warehouses available. The ops manager will keep costs as low as possible. Below prices for delivering a bag of peppers, so just peppers. Warehouse 1 has 60,000 units in inventory, whilst warehouse 2 has 80,000 units in inventory. Calculate the optimal transportation of goods to customers from the warehouses. Okay, so in summary, 4 people have made orders for green peppers, and we can deliver these orders from 2 different warehouses. But it costs different amounts to deliver these orders to the people from each warehouse, depending on where the people stay. So the breakdown you have below is how much it costs to deliver. The first cell is how much it costs to deliver to customer 1 from warehouse 1. Sidebar, I have named these customers. In the question in the slides, it just said customer 1, 2, 3, 4. And I didn't want you to get a little bit confused with so many numbers. So I've given them names just to make this a little bit more personal as well. So we've got Mary, Amma, Mrs. Bucket, and Jude. So Mary from warehouse 1, it would cost $1. To deliver to Amma, it would cost $3. To Bucket, it would cost 50 cents. To deliver to, it looks like Judd is the furthest from warehouse 1, it would cost $4. These are the costs to get to these customers from warehouse 1. At the end of the row, we've got the number of units in warehouse 1. So it says in the question, warehouse 1 has 60,000 units in inventory. So in total, they have 60,000 green pepper bags in inventory. And the same can be said about warehouse 2, delivered to each customer, and the amount of inventory available at warehouse 2. I'm going to just select inventories and the warehouses and make them a different color just to create some distinction between the warehouses and the customers. So let's make these guys purple. Okay, now each customer has an order waiting to be delivered. This is as per the question. But the ops manager must decide on how much of each order to send to each customer from the 2 warehouses available. So it's possible that you could send to your customer from both warehouses if that's the optimal thing to do. So we could split Mary's order and send some from warehouse 2, some from warehouse 1 if our solution says to do that. And our ops manager needs to figure out what the optimal solution is. It's important then to know as well how much each customer has ordered, so that when you are accommodating for the delivery, you make sure they get what they ask for, not any less, not any more. Otherwise, you get bad customer service ratings. So the bottom row is the amounts ordered by our customers. Mary ordered 35,000 units, Amma 22,000, Mrs. Bucket 18,000, Jude ordered 30,000. I'm going to make the amounts ordered and the names a different color as well, so you can see that distinction between the customers and their capacities and the warehouses and their capacities. Let's make this blue. Okay, so in blue, you've got each customer and their capacities in terms of this is how much they've ordered, this is how much they must get. In the rows, you've got the warehouses and their capacities in terms of how many units they have available. Inside, you've got the constraints around how much it costs to get to each customer from each warehouse. And if you think about what you would be trying to do here, ultimately, if you're the transfer person and you want to calculate the optimal transportation of goods to customers from the warehouses, because we're looking at costs in this table, we want to minimize the cost of delivery to all customers. I'm just going to make okay. A decision. According to the question, we want to figure out optimal transportation of goods to customers from the warehouses. So we need to know how much to send out from our 2 warehouses that we've got. So our decision then is going to be how many units from each warehouse to send to each customer. Okay, so for instance, if Mary wants 35,000, we might decide to send 10,000 from warehouse 1, 25,000 from warehouse 2. Okay, if that's the optimal solution. We want to figure out how many units from each warehouse to send to each customer in order to minimize cost, considering the constraints, which are the cost of delivery. Okay, just going to make this visible. Okay, now remember in our decision section is also where we set out our decision variables. So I'm going to just add at the end of this our decision variables are. Okay, and then I'm going to do them below. So we're sending out deliveries from each warehouse. I'm going to start by listing the decision variables from warehouse 1, and then I'll list the decision variables from warehouse 2. And from warehouse 1, I'm going to deliver. It's possible that I could deliver to all 4 customers from warehouse 1. So each customer, I'm going to call customer 1 using C1 and customer 2 using C2, etc. So from warehouse 1 to customer 1, I could deliver from warehouse 1 to customer 2, I could deliver from warehouse 1 to customer 3, warehouse 1 to customer 4. So I could deliver to all 4 customers warehouse 1. I could do the same. I could do the same from warehouse 2. So warehouse 2, customer 1. Warehouse 2, customer 2. I now copy this down. It's going to see the increments in customers and just do it for me. Perfect. Okay, and this is all my decision variables. I'm just going to format it better. I haven't done a great job of the descriptions here in terms of saying that from warehouse 1 to customer 1. You can do that if you'd like to write that out in full. I'm just doing this to be quick. So you could have said here from warehouse 1 to customer 1 and then have that. From warehouse 1 to customer 2 and then have that, etc. Next is our objective function. For our objective function, remember it's a combination of our objective and our decision, and our decisions will be based around these variables, and what we're trying to do is minimize cost. So my minimized cost, my min cost, would be equal to some combination of all of my variables that includes the costs of each variable. So my minimized cost is going to be some cost that goes with warehouse 1, customer 1, plus some cost that's going to go with warehouse 2, customer 2, plus some cost that's going to go with warehouse 3. Let's do this in order of warehouses. Warehouse 1, customer 2. Also warehouse 1, customer 3. Also warehouse 1, customer 4. Then I can go to warehouse 2. Customer 1, warehouse 2, customer 2, warehouse 2, customer 3, and whatever it costs to go from warehouse 2 to customer 4. Okay, now I need to find the costs that go in place of these stars, because remember I'm trying to minimize cost. So I'm going to replace all of my stars now. And I'm just going to scroll up so I can see those costs. So remember this is customer 1, customer 2, customer 3, customer 4. My cost to get from warehouse 1 to customer 1 is $1. So I'm going to replace my first star with a 1. My cost to get from warehouse 1 to customer 2, so I'm still in the first row, is $3. That's to get to Amma. My cost to get to Mrs. Bucket is 50 cents. My cost to get to Jude from warehouse 1 is $4. And I do the same for warehouse 2. So if I go to the next row, I've got the cost to get to each customer. It costs $2.50. I think it says commas, not points. So be careful with your commas and full stops to represent 0.5. Oh, I think Google Sheets uses a full stop, not a comma. Okay, now I'm doing my cost to get to Amma from warehouse 2, which is $5. My cost to get to Mrs. Bucket from warehouse 2, which is $1.50. And my cost to get to Jude from warehouse 2 is $2.50. Okay, so it's interesting that from warehouse 2, Mary and Jude seem to be the same distance. It might not be the same area necessarily, because if you see from warehouse 1, Mary is the closest to warehouse 1, but Jude is super far. Okay, and these are the kinds of decisions you have. So now that I've got my objective function done, just double check that you've got all 8 variables, 1, 2, 3, 4 from warehouse 1, and 1, 2, 3, 4 from warehouse 2, and double check that your costs against each decision variable are also correct. Then you can move on to your constraints. Okay. Now the fun part, this is the fun part. The fun thing about transport questions and blended questions and investment questions is you're going to have to apply your mind. You've already been told these constraints, but you're used to seeing the constraints in a manufacturing question kind of laid out in detail for you. In this situation, your constraints, you might have to do a little bit of thinking around. So for warehouse 1, for example, I can only deliver 60,000 units from warehouse 1. So that's a constraint. I can only deliver 80,000 units from warehouse 2. That's a constraint. The fact that Mary has ordered 35,000 is also a constraint. I can't deliver less than 35 or more than 35 to Mary. I lose money if I do that. So I need to make sure I deliver exactly 35,000 units to Mary, even if they're coming from 2 separate warehouses. Same with Amma, same with Mrs. Bucket, same with Jude. So I've got 2 sets of constraints to think about: the warehouse capacities and then the customer orders. So in my constraints, I'm going to write here warehouse, let's not say capacities, available products at warehouse 1. Now, let me start on the line below. I'll just put a little bit of detail on the side, what I mean by that. So suppose that you did all of your deliveries from warehouse 1 to all 4 customers. It could well happen in your solution that Solver says just only do these deliveries from warehouse 1. If all of them are coming from warehouse 1, it means that each decision variable that relates to warehouse 1, the sum of all of these, the sum of all my decision variables going from warehouse 1 to the 4 customers cannot exceed 60,000. So I'm going to write that below. Warehouse 1 C1 plus warehouse 1 C2 plus warehouse 1 C3 plus warehouse 1 C4 cannot exceed 60,000. So 60,000 is the maximum they can be. So must be less than or equal to 60,000. Okay, and this is assuming that I've done all of my deliveries from warehouse 1. It could also happen that all of my deliveries come from warehouse 2. So I've got to account for the available products at warehouse 2. And this is also exactly the same as above, supposing that all of these deliveries came from warehouse 2 to all 4 customers. Warehouse 2 C1 plus warehouse 2 C2 plus warehouse 2 C3 plus warehouse 2 C4 could not exceed what's available in that warehouse 2, which is 80,000. Okay, so that's my first 2 constraints around my warehouse capacities. These are just explanations so that you understand what I was doing. Maybe let me add here that it must not exceed what's available. Same here. Now that I've done my warehouse capacities, I also need to now make sure that I am delivering what's been ordered by each customer. So I'm going to call this section amounts ordered or products delivered rather, because at the end of the day, we must deliver what has been ordered. Okay, and for my products delivered, each customer must get the amount they ordered. If I send them any less, they're not happy. If I send them more, I'm not happy. So week 1, warehouse 1, C1 plus warehouse 1, warehouse 2, C1. So remember, it's possible that I could send to Mary from both warehouses. I could send for warehouse 1 and warehouse 2. And if I do that, I must ensure that I still give her 35,000 units. So that's what I'm trying to stipulate here. If I deliver to customer 1 from both warehouses 1 and 2, I must make sure that that equals 35,000. In Solver, if Solver ultimately told me that I'm not doing any deliveries from warehouse 2, this would be a 0 and that would be the 35,000. It doesn't matter, you must just stipulate it so that Solver keeps in mind to stay within this constraint. Now I'm going to do this for every other customer. So warehouse 1 to Amma or warehouse 2 also to Amma must equal what Amma ordered, which was 22,000. Mrs. Bucket ordered 18,000. Jude ordered 30,000. So warehouse 1 to customer 3 plus warehouse 1, warehouse 2. Customer 3 is equal to 18,000 for Mrs. Bucket. Warehouse 1 to Jude plus warehouse 2 to Jude must equal the 30,000 that he ordered. Okay, and that's all of our customer orders catered for. Trying to make sure that the customer gets exactly what they ordered. I'm not using a less than or a greater than or equal to because that allows me to exceed or go under that order amount, which is not a preferable solution for the customer or for the supplier. Last but not least, non-negativity, integers, and this applies to all. So I'm just going to put a star here and say all. You already now know how to do non-negativity and integers. It's selecting all of your variables and saying they must be greater than 0. Selecting all of your variables and saying they must be whole numbers. You can't deliver half a pack. Okay. I'm not going to write those out in detail. And that's the LP setup for the green peppers question. At this point, you should be able to more or less think about how to then go and do your solver setup. Just a hint that it's easiest to do it in this format. I'll detail how to do this in the next video. Good luck.